Hi, I'm Gary Sieling. I'm a software architect at IQVIA, the human data sciences company. We build SaaS applications for regulated industries, and I'm involved in all the different parts of our application stack, but I have a particular interest in databases. So today I'm going to talk about using Word2Vec within Postgres. So I have three general topic areas within this. I'm going to talk about some of the trends that I've seen from doing research in terms of how people are integrating machine learning with relational databases and what some of the trade-offs are. And then I'll show some specific examples around Word2Vec and Postgres using job search as an example use case. So to start off, as an example of something that you might want to do if you're doing job search, let's say you wanted to find, let's say I was looking for a job. I would look for jobs in my area probably within some sort of driving distance computation. Presumably I would want something that was like what I have, but with a higher pay and requiring a roughly comparable skill set. And so this really encompasses three different features of a job. One is the location. So starting from where I'm at, I have some sort of computation I want to do. I have a really simple numeric search, and then I have some concept of semantic similarity between what's in my resume currently and maybe current or past jobs. And these three restrictions highlight where we might get some value of combining machine learning tools and relational databases together. So if you can find what you want to be able to do is to find some way to bring the machine learning applications that you have into a data warehouse. If you have a large quantity of data, a lot of times there's already a place where the data that you have lives, and you need to have some interaction with these external tools that are being built. And the advantages you get out of this are you get access to all of the relational database features that you might already have. So in the case of Postgres, there's a good geospatial extension that you can use. There's full text search in the database already. There's some other custom data types that you can use that are really useful for specific applications like trees, which are useful for things like implementing security. There's ranges, you can put JSON in the database and so on. And then once you get into the building a production application and you start to have performance tuning type issues, you can use a lot of the traditional database functionality like different index structures and the ability to create materialized tables and control things like what kinds of disks the data is stored on, and that sort of thing that you might be accustomed to in a relational database. And so combining these two things together can be really valuable. And there's three kind of patterns that people use. One is the older style of data warehouse where you take a big database and you just buy the biggest piece of hardware you can buy or the biggest VM you can afford. This has the advantage of being a little bit simpler to model locally as a developer. You can also take that large database and split it up into a bunch of different ones and then divide the work up in some way. Or you can flip the architecture around completely where each component of the system is its own product or set of servers or something. AWS advocates for this particular type of design if you're building really large systems because you can control a lot of things to a great deal of fine grainedness. So for instance, you could upload a bunch of CSV files, JSON files, etc., Parquet files to S3, run SQL queries directly against those with a tool like Athena, run batch processing jobs to convert those back and forth with the product in AWS called Glue, and then maybe do some stored procedure style work with Lambdas. And all three of these approaches have some value, and it depends a lot on the system you're trying to build. So I'm going to focus more so on how you can get the machine learning tools into a relational database. So this is maybe a little bit smaller scale than some massive data warehouses, but I think there's a lot of potential for this because you can do a lot of interesting things. So three examples of open source or products that you can use that give different trade-offs in terms of functionality. There's a tool which lets you do things like put decision trees into Postgres, and so you can train and do predictions based off of things that this tool has learned from your data just in SQL queries. Google has a tool called BigQuery, and they have a sort of higher level construct where you can create a model, and that represents some sort of machine learning model that you created, and then you can run predictions from within the SQL queries that you're running. An alternate approach is SQL Server has an add-on that you can use to run R code, and then you can write stored procedures. The value of that is you've got stored procedures which run on the database, so very closely located to the data that you're operating against. You can write a lot of custom stuff that way. So these are all just like some different examples. And I'm going to focus here on working with vectors specifically, because as a data type, these are a little bit more challenging because you just have a volume of data that you wouldn't necessarily have with something like, say, categorizing a list of documents into topics or something. So the example of this with Word2Vec, one of the popular pre-trained models is this Google News data set, which has 300 dimensional vectors for 3 million words and phrases. So if you imagine that as a database table, it's not enormous necessarily in terms of what exists in the real world, but it's a big enough data set that there's a little bit of weight to it, and something that you may run into some tuning issues if you're not careful with how you handle it. But a lot of the research that I found in terms of custom database indexes revolves more around things like image search, because the algorithms like SIFT will also generate some sort of vector object, and so you can also stick those in a database. And for the amount of image data that's out in the world, you can imagine that this could scale up dramatically beyond what is in Word2Vec. And similarly, if you have data from audio or something, you could imagine some pretty large data sets, even once you get beyond things like this Word2Vec text thing. So the challenge here is you, in essence, have something which is one giant matrix, and there's different ways to store this and different ways to read it and load it into memory. There's a whole bunch of people working on that particular category of problems. If you look in the space of Python utilities, NumPy has the construct of just storing something as a giant matrix on disk. There's also a tool called HDF5, which is a similar concept, but you can store other data types at the same time. In the Java world, the Deep Learning for J has an implementation of Word2Vec, and they can do things like store things in JSON and read it back, which is, for a data set this size, is really memory intensive, and it takes a lot of time to start up. You might expect a tool like Lucene to make it easier for you to use vectors, because it's already a full text system, and it is doing something implicitly, which is a lot like things you might do with Word2Vec. But from what I've seen so far, they don't have a data type which is large enough to store the kinds of vectors that people would normally generate with something like Word2Vec, although I think there's people who are working on making that better. So what we're going to end up doing is sticking this thing in Postgres using a tool that a team at Facebook is writing, which is basically a custom standalone index called FAISS. This provides a storage technique, so you can make just plain files, or you can store it in Postgres just as bytes. So this byte A type, we're going to basically have a serialized vector in each row in a table in a database. And FAIS is going to provide us with some functions that we can call to see how similar vectors are, to see compute distances between them, and so on, but do it in a way that's really fast. And so what this library is described as by the team at Facebook that makes it is a library for efficient similarity search and clustering. Common operations that you would normally see that you would kind of want to expose on vectors are things like taking a matrix and reshaping it, computing distances, like I said, summing a whole bunch of these together or averaging them, and then finding the nearest vectors to something that you have. The data set I'm going to use for these examples is about 30,000 job postings. I just crawled some things off Indeed, basically picked a bunch of cities and then stuck them all all of the job listings in a table. So when I show the examples, that's where this data set came from. It's pretty broad range of different types of jobs. So it's just whatever's in the city at the time I ran the script. And the goal here is we're going to take a resume and we want to compute how similar the resume and the individual jobs are. The reason that we're using Word2Vec specifically is because it gives us this concept of meaning rather than working on tokens the way a full text search, traditional full text search would do. So for instance, in a job posting, you would see a word like JavaScript and CSS. And I might say in my resume, well, I'm a web developer. Those two things are essentially the same, but you don't see any overlap in the words. Word2Vec will help you pick up on that. You can also use this to punish categories of concepts that you don't want to see in something. One of the things that you'll find if you read some of the papers on Word2Vec is that you can take all of the terms in a document, average the vectors together, and you'll get something which is representative of essentially the average meaning of the document. So if you did that on a job posting and you did that on a resume, you could compare the job posting and the resume and have some sort of measurement of how semantically related the two different documents are. This also means that you can say how dissimilar two things are. And so if you had a list of things which match the search query, you could find things, you could sort of try to maximize the distance between the individual search results, which would give you like better search diversity if that was something that was valuable. That's, for instance, if you were doing e-commerce and you wanted to give somebody listings of shoes and you wanted to give the most different kinds of shoes so that they could kind of help train the user to refine their search, that in that kind of case, the diversity of the search results is really valuable. So from a practical perspective, what we're going to do is we're going to take my resume, we're going to tokenize it into the individual words. We're going to find the word vector for each word. We're going to average them together, and that'll give us a vector which represents the document. We're also going to take those terms and we're going to, for each one of those, search within the Word2Vec model, find words which are close to the ones that we already have so we can generate effectively synonyms. We'll search for all those synonyms in the job postings with full text search. Then we'll apply the same tokenization and averaging process to each document or each job posting. We'll compare the distance between the job postings and the resumes, and that gives us the similarity metric that we can sort on. This isn't a perfect system, but it's a good basis for understanding how you can do stuff with these tools. Conceptually, though, a lot of the work that I just described is things that you would do over and over and over again. You're not going to do this for every time someone searches for job postings on a search engine. Realistically, you want to compute as much of this as you can in advance because it does take some time for the system to, if it's loading up a model or loading up data from disk or something, there's a lot of tokens or a lot of words in each resume, and you don't want to do this each time. So we're going to build some tables in advance which have this stuff pre-computed. The tool that I'm using to bring FAISS into Postgres introduces this function called tokenize, which splits the document on spaces and then gets the terms, averages them in a way which is really fast. And so you can, this tokenize function is actually doing a lot more than you would think. This is actually just returning that average value that we wanted. So we're going to create a table for resumes based on that. We'll do the exact same thing for jobs. And so now we have two tables that we can compare. We can join these two tables together, compute cosine similarity between the two values, and then we can sort on this. And so one thing to notice here is that this is just a Cartesian join of all the resumes and all the jobs in the system. You probably, if you're building a real system, you would want to have all those other filters on things like geography and full text and maybe category of job or something, so you can really filter this down. Because this is doing a Cartesian join, it's going to take some effort for the database. So you really want to reduce this as much as you can in advance. But for this example, this illustrates the point of what we're trying to do here. One of the issues, though, that you almost immediately will run into is that Word2Vec is just picking up on what the words are in your resume, and it doesn't really know what's important to you. So for instance, I've worked in life sciences for some time, and it will pick up words like clinical as being important, but I'm actually a software developer, software architect, web developer, something like that. And so I really only care about the words related to software. I don't care very much about the words related to life sciences. And so this is also a problem that we can fix with Word2Vec with a separate query. We can take, what we're trying to do here is to take the resumes database table, take each word in the resume and compute how similar that individual term is to the entire resume. And so we could take this and then just take the top terms in the resume. So a word like clinical should get dropped out because in previous jobs, if I worked in different industries or something, it's going to say, hey, that's not really that related to the general theme of this resume. And so this gives us a way to maybe hone in a little bit on what the person's actual intent is and what they're looking for in a job. So I didn't talk too much about the tool that I'm using here to get this these functions into Postgres. Someone, I guess a researcher, wrote up some hooks to bring FAISS data into tables in Postgres and to hook the SQL functions in. And if you go down the road of using this GitHub project, there's a whole bunch of different functions that they provide you, which give you the ability to trade SQL query performance for precision in the results, which I think is one of the things that's kind of compelling about this particular tool and the data set that's behind it. If you look this up, you'll find this fairly intimidating label for what the tool actually does to optimize the query. So it's inverted file system with asymmetric distance calculation. And in essence, there's two pieces to this. The asymmetric distance calculation says, hey, what if we took all the vectors in our model and say we put them into a grid like on graph paper? We could say, treat all the ones that are in the same cell basically as equivalent. We can compute the distance. Instead of computing distances between individual vectors, we'll compute them between cells in the grid, and thus we have a lot less data to hold in memory. We would compute distances by saying, what's the center of the cell in the grid? What's the center of this other cell? Use the distance between those two. That introduces some error, but it gives you a lot less data to hold on to when you're doing the computations. But practically speaking, when you're working with something like large data sets of Word2Vec, for instance, you'll find a lot of like clusters of points, kind of like star constellations. And so you don't want to put them in a rectangular grid, because what you'll end up is finding that there might only be like a handful of little clusters, and you've inadvertently destroyed some data that you didn't mean to do. And so in essence, these things, there's a field of research where people work on hashing this information in a way that groups, that tries to keep each cell having approximately similar number of vectors within it. So they're not rectangular, they're differently shaped and differently sized. And so the trade-off that you're making there is you can be a little bit more accurate in terms of computing distances between these things, because you're not like combining all of the vectors, say, maybe into one little cell. On the other hand, some of the cells are going to be a lot bigger than others. This also means that you can compute a distance function between either two of the cells, or between a vector, like just a vector that you've got coming into the system, and one of the cells, because you can say, take the center of the cell and compute the distance between the center and the vector. That also introduces a certain amount of inaccuracy. And so the papers that are written on the subject talk a lot about how to deal with that inaccuracy as much as possible. So this library encapsulates within it functionality to kind of deal with that as much as possible. So when you're calling these functions, in essence, you get to choose, do you want the more or less accurate versions of these functions? Do you want to have exact distances? Do you want to have approximate distances? And when you and then you can make some trade-offs, which you'll have to test on your own data to see what gives you what you're looking for. But this has a lot of power that you could use to do some experiments. So far, though, the system that we've set up has a couple issues. It doesn't consider how frequently each term or concept occurs sort of globally. We might want to say something like terms which aren't really related to jobs at all shouldn't count much at all. Like in traditional full text search, you might have a list of stop words like the and of and something like that, and those shouldn't really matter. It doesn't really help us find jobs that are the next step for someone in their career. It also doesn't give you some concept of how old a job in the resume was. If you had a job 10 years ago, you probably want to discount those. So these last two things are kind of related. You want to probably weight the terms which are earlier in the document heavier than the ones that are later. So realistically, we're going to have to do some extensions to the previous queries that I showed. I'm not going to go through all the different things that you could do here, but this is just to give some examples of what you'd actually have to do to get this to work in a thorough fashion. The older full text algorithms use this concept called TFIDF, which is, in essence, you want to take into consideration how frequently a word occurs in a document and how frequently it occurs in general in the whole corpus to determine how much meaning it really has for a query. So a query here, it's as if we've pasted an entire resume into a Google search box, and then every document is the job search. So here we want to take every word in the resume and say, how frequent is it in this resume? How frequent is it in the job posting? That gives us some concept of weight. The downside of this is that, at least at the moment, I think Postgres doesn't do full text this way, so we have to kind of implement something on our own. And that's actually okay, because we want to be able to combine this concept of token frequency, which is the individual words, with the meaning frequency. So we want to say, like, maybe JavaScript and JS are related, and the fact that JavaScript occurs really frequently, but maybe JS doesn't. We still want to treat those as effectively very similar. And if we can combine TF-IDF with Word2Vec, we can get some good results. So here I've taken and said, let's imagine we make two new tables. We'll make a table that has every word that we've ever seen. We've called this global terms. We've counted how frequently every word occurs, like the total number of occurrences of each word, and then the total number of documents each word occurs in. That's what DF is. And then we'll do the same thing for the resume. We'll count how many times each word occurs in each resume. And then from these two, we can take these measures and compute a value for like the sum of all the terms in a resume. And you can use this, then combine that with the job posting as well, and you'll get a TF-IDF score. You can then take and times that score by the similarity score that we did before, and that gives you some way to take the meaning, like the total sum of all the meanings based on how frequently that they occur. Basically then we can take and build our summary score based on these two things combined and get an interesting result. So here I pulled out some of the search results for one of these. You can see that the first three look like they're probably appropriate. They look like, granted they're two intern positions here, but the first three look like they're technical positions. The second three don't. So there's clearly some more room for tuning this. And it does take some time to compute. So you wouldn't necessarily do it exactly this way. But this shows, I think, some of the technique that you would need to set this up. So if you wanted to improve upon this, I think you would want to investigate probably tuning the TF-IDF implementation that I did above. What you'll find if you read papers is that a better approach is to do the TF-IDF search first, using, say, a big list of synonyms like I described before, but then cap the results. So let's say we search for job postings, jobs that I might apply to, pick the first 1,000, then resort those based on the similarities, the similarity score that we generate from Word2Vec. Basically, we start from like reasonably high quality results and we make them more high quality. That works really, really well, much more so than applying Word2Vec on the whole data set. At least that's what I found. And if you wanted to, say, have diversity in the result set, you would want to apply that searching and capping thing repeatedly. So you might say, take the first 1,000, sort by how close the search result is to your query, cut it to 500. Then do the same thing again on the diversity thing, find a row, find the least similar row to it. Find a third row that's as little similar to the first 2 rows as you can, and so on, and that will give you a good result. So if you wanted to apply a series of different Word2Vec concepts to it, you would essentially do this search and cap thing repeatedly until you got enough rows, or until you got the result you were looking for. It's also worth noting that there's different implementations of how you can train these vectors. So FastText has become popular because it's a nice, really fast command line utility you can use to train Word2Vec models, but it's more syntactically oriented from what I can see. So they incorporate the individual letters that you see in words, and so it has a better ability to deal with things like spelling errors. So if that was something you were concerned about, then FastText might be a good option. StarSpace is also another tool by a Facebook engineering group. And the goal of this is to be able to train more towards categorization system. So you might say, like, you like these 6 Facebook pages, here's a 7th that you might like. And so my suspicion is that this is, for something like job search, this is probably, this path is probably a good one, whereas something like FastText is good if you were trying to help people, like say you were building a travel site for people in Vegas and you knew that people were typing on their phones and were going to make typing errors. So you kind of have to decide what fits your application. The research that I'm doing here is for a search engine that I built called findlectures.com, which is just a search engine for talks, oriented around kind of helping people discover things. So think of, you're walking around a library and you just pull books down randomly. The goal is to kind of replicate that feeling in a search engine, which is a little bit different than traditional search. We'll, after this, send out the slides. There's a couple paper links in here papers that I found helpful when I was reading this. And then if you want to contact me, here's my information. If anyone wants to post questions, feel free to post things in the chat and I'll wait around for probably 10 or 15 minutes. Thank you for listening. And if anyone has any questions afterwards, feel free to shoot me a message or talk about any topics you're interested in beyond this. This is kind of I think a niche topic where you have to have a data set to really set up to be able to do anything. Okay, so first question is, are you using Scala for NLP? What I've tended to do is I have used Scala for it. I've done a couple talks where I was using Scala and deep learning for J specifically. Sometimes if I'm just doing experimentation, I think there's probably more code examples in Python, and so typically what I would do is just follow whatever someone's done in their paper if that's possible. But I like Scala as a language for a lot of this stuff when it's appropriate. The question is, what about evaluation metrics and benchmarking? What I found when I was doing the research for this, the way that I've seen people doing evaluation of the results for search engines is to have raters who do a bunch of search results, rate the results, and kind of score them to say, yeah, this is a good result or a bad result. And also the ranking algorithms, which are trained based on that, a lot of times are trained off those data sets, but you have to have access to a team and a big enough search engine that does that. So what I've ended up doing is not so much, I honestly can't say that I've attempted to come up with evaluation metrics on these. What I've done is I basically just follow the papers that some of the big teams do. So Bing in particular has a research team that puts out a lot of papers and they have a lot of good material. So basically what I try to do is to follow what they do as best as I can. And when it seems like the results are good, you're spot checking the results. There's also a guy who's a researcher at DICE who does a lot of talks at the Solar Lucene conferences that are pretty good. And so a lot of his evaluations based on their data sets are good to follow as well. So unfortunately, I don't have like a great answer for how you would do that on your own. There's some consulting companies that do the evaluation type things. They'll hire teams of people to test search results and give you metrics. And there's also some companies. There's a company in, I think, Virginia that's really focused on just search result quality. And so they're good people to talk to too. There's a book called Relevant Search, which is really good as well for understanding some of the dynamics of what goes into search result tuning. All right, if there aren't any other questions, I'm gonna shut down the recording. You guys can enjoy the rest of the conference.